Go ahead.
So hi everyone, I'm Sid from Yale and I'll be talking about this paper with my advisor Andre Wibisono on the fast convergence of Phi-Divergence along the unadjusted Langevin algorithm and the proximal sampler. So let me jump straight in. So consider the task of drawing samples from a target distribution nu. Very fundamental question arising in many fields, for example in Bayesian inference where you want a sample from the posterior distribution. And a common approach is to construct a Markov chain with nu as the stationary distribution and then draw samples after some initial burn-in time. So suppose you have such a Markov chain P, the question is when do we obtain a useful sample? And the mixing time of the Markov chain tells us exactly that. In particular, it tells us when the law of the last iterate is close to the stationary distribution, so it tells us how many samples to discard before we obtain a useful iterate. And you can measure the mixing time in many choices of distances or divergences, for example, total variation, KL, chi-squared. And the family of phi divergences include all of these examples as special cases. So what are phi divergences? Well, they are parameterized by a convex function phi, and so the phi divergence between mu and nu is the expectation with respect to the second argument times phi of the density of mu with respect to nu. And different choices of phi give rise to the examples, for example, those that I mentioned on the previous slide. And we will consider twice differentiable and strictly convex functions phi. And our goal in this paper is to establish mixing time bounds for two popular sampling algorithms, the unadjusted Langevin algorithm and the proximal sampler in Phi-Divergence. So recall that nu is alpha strongly log concave if the potential F is strongly convex, and nu is smooth if the potential F is L smooth. And we say that nu satisfies a phi Sobolev inequality with constant alpha if for all distributions mu, the phi divergence between mu and nu is at most the phi Fisher information, where the phi Fisher information is this expression here. And different choices of phi give rise to different isoparametric inequalities. For example, you can get a log Sobolev inequality or a Poincare inequality. And a distribution which is strongly log concave implies that it is phi Sobolev for all phi. And a phi Sobolev inequality assumption on nu also implies the fast convergence of phi divergence along the continuous time Langevin dynamics, which is what I will describe now. So in continuous time, the Langevin dynamics is the following stochastic differential equation, where the drift is the gradient flow for minimizing f, and we have Brownian motion. It admits nu as the stationary distribution, and you can also view it as the gradient flow for KL divergence in the space of distributions with the W2 metric. And under the stationary distribution satisfying a phi Sobolev inequality, we have the fast convergence of phi divergence. And this generalizes popular regimes such as mixing of KL under log Sobolev or of chi-squared under Poincare. And to see the proof of this lemma, you can compute the time derivative of the phi divergence, where rho t is the law of xt along the dynamics. And you get that it is equal to minus phi Fisher information. Then under nu satisfying a phi Sobolev inequality, you can upper bound this by the divergence and then integrate to get the desired statement. But this is all in continuous time. We need to discretize in time in order to get an implementable algorithm. And in some sense, the simplest possible discretization is the unadjusted Langevin algorithm, which just considers the forward discretization of Langevin dynamics. And the update here is like a gradient descent step for minimizing f, and then we add a Gaussian random vector corresponding to the Brownian motion implementation. And it recovers the Langevin dynamics in the limit, of course. However, note that it is a biased algorithm. So the stationary distribution of ULA is not equal to the target that we wish to sample from. And this is a very well-studied algorithm with a partial list of works here. In this paper, we will study the mixing time for it in phi divergence. But note, yeah, okay. So now our main theorem for ULA is the following. So suppose that the target is smooth and that the bias limit satisfies the Fy-Sobolev inequality. Then we have the exponential convergence of Phi-Divergence to the bias limit along ULA. And the bias limit satisfies the Fy-Sobolev inequality when, for example, if the target distribution is strongly log concave. In particular, this theorem guarantees mixing in all phi divergences when nu is SLC and smooth, but it is to the bias limit. If you want to really get mixing to the target distribution nu, one thing you can consider is the proximal sampler, and that is what I'll talk about now. So the proximal sampler considers a joint space, and there is a joint target distribution nu xy on this space. Note that the x marginal of this joint distribution is the target distribution you wish to sample from. So if you could sample from this joint distribution, then you could drop the second half and then get samples from the true target distribution that you wish to sample from. And after defining this enhanced space, the proximal sampler is the following Gibbs sampling algorithm. So it will iteratively sample y given x and then x given y. The forward step, which is sampling y given x, is easy to implement as it corresponds to sampling from a Gaussian. And the backward step is possible given access to an oracle called the restricted Gaussian oracle, or RGO. There are various ways to implement an RGO, for example, via rejection sampling, but you can do fancier things. This is an unbiased algorithm, so the stationary distribution is indeed nu xy, and once again, it does recover Langevin in the limit. And amongst prior work, this paper studies mixing time in KL, chi-squared, and Renyi. Our main theorem for the proximal sampler states that under a Phi-Sobolev inequality assumption on the target distribution, we have exponential convergence of Phi-Divergence to the target distribution. And there is no smoothness assumption here, as it's for the ideal proximal sampler, i.e. the proximal sampler given access to an exact RGO. I will say that in many RGO implementations, you do need to assume some smoothness on nu x. And it does recover the exponential convergence rate for Langevin in the limit. And once again, you can consider RGO implementations and obtain concrete iteration and complexity bounds. So now let me sketch the proof, which is via strong data processing inequalities. So the data processing inequality from information theory states that information cannot increase along a noisy channel. And viewing a Markov chain as a noisy channel, it says that if you apply the Markov chain to mu and pi, then the divergence between their outputs cannot be greater than that between their inputs. The strong DPI makes this concrete. So define the following contraction coefficient. We say that p comma pi satisfies an SDPI if this contraction coefficient is strictly less than 1. The fact that this contraction coefficient is less than equal to 1 is guaranteed by vanilla DPI, but here we want the contraction to be strictly less. And in particular, this implies that for all mu, we have a drop in the phi divergence by at least a contraction coefficient factor. And I claim that we can get mixing bounds if we have an SDPI. So suppose nu is stationary for p, and suppose that p comma nu satisfies an SDPI, by which I mean that this contraction coefficient is strictly less than 1, then this implies the fast mixing of pi in phi divergence, because this is the quantity you wish to bound when you want to show a mixing time guarantee. And then you can unravel it by applying SDPI k many times, and each time you apply the SDPI, you pick up a contraction factor. And so you get this exponential rate. SDPI-based methods have been implicitly used to show mixing for Langevin-style algorithms. In this paper, we explicitly use it for the ULA and proximal sampler in phi divergence. And let me briefly sketch the proof for ULA. The key lemma bounds the contraction coefficient for ULA under the same assumptions as the theorem. We show that the contraction coefficient is strictly less than 1. In particular, it is this explicit quantity. And the ULA update can be decomposed into 2 steps. So there is this gradient descent step, and then there is the Gaussian noise step. And the update in the space of distributions is as follows. So the blue part corresponds to pushing forward the measure of xk, which is rho k, by this map I minus eta grad f, which I will also call G. And then adding independent Gaussian noise corresponds to convolving the density by a Gaussian. And to bound the contraction coefficient, note that we want to bound something like this. So this ratio. We can apply the form of P for ULA and get that it is exactly equal to the push forward plus Gaussian noise, push forward plus Gaussian noise. The push forward step is deterministic, so it does not change the divergence between rho and nu when you apply it. When you convolve both with a Gaussian, you can view it as evolving both distributions along the heat flow for time 2 eta. And that is what gives you the contraction in divergence. So in particular, the contraction of phi divergence along the full Markov chain is induced by the contraction along the heat flow. And more explicitly, you can define the marginal distributions along the heat flow to be rho t and nu t, and you can compute the time derivative of phi divergence. This is equal to minus 1/2 times the Fisher information. This is similar to what we had for continuous time, but here both are evolving, rho t and nu t. And then under nu t satisfying a phi Sobolev inequality, you can upper bound this by phi divergence and then integrate to get a contraction bound. So to conclude, we study the mixing time of ULA and proximal sampler in phi divergence under a phi Sobolev inequality assumption. This generalizes popular mixing time regimes, and the proof technique is via SDPIs for the Gaussian channel for ULA and for both the forward and the backward Gaussian channels for the proximal sampler. Thank you, and please drop by the poster to talk more.
Thank you. Yes, so my understanding is log Sobolev inequality will give you like Gaussian concentration, and Poincare will give you exponential style concentration. So I was wondering, with these results, can you go into the heavy tail regimes with the right choice of phi?
I think heavy tail is difficult. So the Poincare inequality is in some sense the weakest phi Sobolev inequality. You can show a weak Poincare inequality and then strengthen it to get a mixing time, but I think getting convergence or like mixing for heavy tail distributions is a separate field, and some people do work on it. But I don't think these methods off the top, directly give you mixing for heavy tail distributions.
Okay, thank you.